Okay, sir. We will start the session, sir.
Yes, ma'am. I just initiated the presentation. Ma'am, are you able to see the presentation?
Visible, sir. Visible,
Uh,
visible.
okay, ma'am. Okay. So now we are going to have a hands-on experience on creating the CNN and also taking the pre-trained models. So our agenda is going to be this. So first we define our architecture. Okay, so we create an CNN architecture from the scratch to deal with a CIFAR 10 dataset, which contains 10 classes. Okay, and then following that, we will load and use a pre-trained model, such as a very huge architectures like AlexNet and ResNet, to make an inference. Given an image, we pass that image to the model, then the model will predict the class of that image. And we can, of course, make use of those architectures for our own applications. But since the architecture is really large and also the number of classes is also large, training it on even a moderate GPU will take a longer time. But if you have an access to powerful GPUs, you can use that as well. So finally, we may attempt to fine tune the existing models for our own applications. Okay. So if time permits, we will cover all these three. But what I feel is that the first one is very, very important. That is, we should be able to create our own architecture and train it with our data set. So once if you understand all the process and the components involved in creating this architecture on our own, then the second one and third one is very easier to learn and execute. Okay, so now let us focus on this CIFAR 10 dataset and architecture. And before that, what I would like to insist is that we are going to deal with numbers, right? So if it is just a single number, 5 or 10, dealing with a single number is quite easy. Even with a vector is quite easy. Is quite easy. But we are going to deal with millions and millions of numbers stacked in different dimensions. Okay, so we should have a good knowledge on understanding or creating these type of tensors. Okay, so once if we go beyond 3 dimension, okay, so if I just deal with single number, so if I allot x equal to 5, then it is going to be a scalar. So if we put a sequence of numbers inside a bracket like this, we call this as an vector. Okay, then you can arrange the numbers in a matrix. So we in a grid we call that as an in image processing it is an image, but in general it is simply a matrix. But as we go along, we will have three-dimensional or from 2D we move on to 3 dimension. Okay, so usually image is a 3 dimensional tensor where we have x, y, and z, both spatial and as well as depth. But still, if we move on into the convolution layers, you can see the depth of around 256. All these things are possible. But when we go for deploying RNN something, we will still move on to the other dimensions. Okay, so what I wish to finally, the key takeaway is we should be able to create all these tensor and we should be able to manipulate all these tensor. So what do I mean by that is creating this matrix is quite easier. That's not a big deal. But suppose if I want to have an access only these elements, how can I do that? Or if I want to access the diagonal elements of this matrix, how can I do that? Okay, so how can we achieve that? So as long as it is a 2D, the operations are easier because I have only 2 axes. But if you go into third axis and 4 and 5, then bringing in elements or a sequence of elements or accessing in sequence of elements from a particular dimension, all this becomes an essential skill set. Okay, so you might wonder, do we really know all these things? Of course we have to know all these things, because if your end objective is to just develop an application and run it on a server, you don't want to bother about creating an architecture from the scratch. then you need not to bother about all these things. But if you are a research scholar, or if you want to really dive deep into how this uh, architecture is learning things, okay, say for example, we have multiple layers. I want to know how the parameters in a particular kernel is changing over epoch. Okay, so for each iteration, the parameter in a kernel is keep on changing based on the gradient, right? I want to observe how this gradient is changing over a period of, or over an iteration. Okay, if that is the case, then if I have created the architecture from the scratch, then I can do it because I know how to access an element and how to make a callback to that particular kernel. All these things I know now. Okay, so that is quite easier. So you can do a lot of stuff if you create a structure on your own, and that is you will have a complete freedom to carry out. You ask any research question, and then if you are creating an architecture from your own, you can answer that research question. Okay, or you can observe what is going on in the entire architecture, the information flow, everything. But if you prefer to use high level API, okay, say like Keras, even PyTorch and TensorFlow, all of them are providing high-level API where they hide the implementation detail. So they act as simple black box. So in such a case, you don't have a lot of freedom or flexibility to do so many things. Okay, so it all depends on what you are going to do, what you are going to do with this deep learning architecture. Okay, but I'm going to focus on from the research perspective because all of us are either faculty or research scholars, so it would be better if we look into the research perspective. Okay, so I'm going to create an architecture from the scratch, and again, before developing an architecture, first we must have a good understanding about our data set. Okay, so here we are considering a CIFAR data set which contains 10 classes. So you can see these class names, airplane, all these things, right? So for each class, there are some sample images displayed here in a grid. So the size of the, so what are all the information you should know? So how many training images are there? Okay, so the training images are going to be 50,000, right? So remember each image is of size 32 cross 32 cross 3. Okay, I think around some 1,000 elements are there in an, or 3,000 elements, 3,000 pixels are there in a single training example. So we have 50,000 such examples. Okay. Similarly, testing set contains 10,000 examples. And then we need to do few more things like what is the batch size and what is the number of classes, all these things. So for the sake of illustration, we are going to set the batch size as 4. Usually it is 32. If it is really a larger image, say for example, if the spatial dimension of the image is say 512 to 512, then oftentimes your batch size will be around some 16 or something. Okay, so if it is a smaller image, you can go all the way up to 512. You can set batch size all the way up to 512. Okay, so one more thing that you should be aware while you load your data samples into the memory is you should not load the entire data sample all at once inside your RAM memory. Okay, so this is one of the important thing that we all have to remember, because this is what to say, you will unnecessarily crash your system. Because if I have, say for example, 12 GB of RAM dedicated for computation, and traditionally, say for example, if I use a data set from the Coco or Pascal uh, for object detection, all these things, so their size itself is 12 GB. Okay, so the recent size 2018 or 19, the entire data set size is 12 GB. So if you load inside this RAM memory, what happens is they will be get decompressed and they will take more than 12 GB. Okay, so even the CIFAR data set, if you load all the images into them, I think more than 2 to 3 GB will be occupied. Okay, so if you load entire data set all at once. So for that, all the framework, all the deep learning framework, PyTorch, TensorFlow, Keras will provide a functionality which helps us to load all those data from the folder when it is required. Okay, so you keep all these data in your external hard disk. Okay, which can have a memory space of 1 TB, or you can store them in your Google Drive if you have an infinite storage, access to infinite storage. Okay, so however, you are storing your data in a separate storage device, and then you load the data if and when required. Okay, so even though I have 1 million images, and if I am going to train uh, with batch size set to 16, then I have a utility functions which helps me to load 16 images from this 1 million images for one iteration. Like that, it will load all the images over some 10,000 iteration. So we need to do this to avoid or uh, to fully utilize the RAM, okay, properly. Otherwise, the RAM space will be consumed by the data samples itself. So the computational time will be much higher. So this is one thing that you have to be very cautious about. So I heard that you have been already exposed to this PyTorch framework, and I'm, of course, many people are in favor of PyTorch than TensorFlow for so many reasons. So either it doesn't matter at all whether you are preferring PyTorch or TensorFlow or Keras for your task, because once you know the components involved in your architecture and their operations and their parameters, all the frameworks uh, provides those functionalities, so you can make use of them. More or less their functional name will be similar. Okay, so you won't feel much difficulty once if you understand the concept. So PyTorch again have many modules. So these are all the list of modules available in PyTorch. And if you wish to use PyTorch for computer vision application, you this module will support in many ways. Torch Vision contains the pre-trained models, dataset. All these things are in this Torch Vision module. Okay. So apart from this, you can see there are many modules, but we are not going to use all of them at all the time. Again, I will use an analogy when I teach this to students, right? So you can think of the framework as a supermarket. Okay. You are getting into the supermarket. Okay, because you want to accomplish something, you want to buy something that is required. Maybe you want to cook something, you want to buy the vegetables or some grocery items. So if that is your task, once if you enter into the supermarket, you will move to the, even though there are many sections, right? Stationery section is there, all these things are there, but you will move to the particular section you want to go. Okay, like the grocery section. Okay, and then even then you will start picking up the required things. Okay, you will not look into all the products available in the grocery section, and you will never look into the stationery sections, right? That is not unnecessary. So the same thing is here. So PyTorch is kind of supermarket. Okay, so all these supporting modules are kind of all these subsections available in the supermarket. The only main section is this torch. Okay, so if you learn uh, the functions, this is actually a data structure. So if you learn this torch or the functionalities available from this module, it will be enough to develop any deep learning architecture. But you have to create it from the scratch. Okay, you have to do, you have to define the code to take a convolution, all these things, but it is possible. The other module that is common across all deep learning architecture, whether it's CNN or RNN, is this torch.nn module. Okay, only these two are very important modules. So other than that, there are few which you can take a look into. Okay, so you can take a look into this torch.utils.data, which helps us to load the data stored in my hard disk. Okay, so other modules are not necessary for the time being, but if required, you can take a look into it. Okay, oftentimes I have students who start studying the entire documentation without any aim. Okay, which means it will never complete. You cannot read all the functionalities available in PyTorch and understand it. Oftentimes you don't know what that function is at all because it is developed for some other application. You don't need to bother about that one. Okay. So now let us pay our attention to these two torch. So if you are already having exposure to this NumPy package, which helps us to create it's a numerical Python, which helps us to create a vectors and n-dimensional tensors. Okay, so whatever I can do with NumPy, I can do with torch. Okay, so if you have learned NumPy to the core, you can reproduce the same with torch. So only difference between NumPy and torch is that torch runs on a GPU, NumPy won't. NumPy won't support GPU. Okay, it only run on a CPU. So like NumPy, we have so many data structure, tensor data structures, create all these operations. Like, so in NumPy, you might have seen all these random number generator, math operation, everything is there in torch module alone. Okay, so I'm repeating again. So if you know the torch model to the core, you can create any architecture. Okay, you don't need to look into any other module. You can create any architecture on your own. That is what we can talk about this torch. Okay, so then what is this torch.nn? Okay, so this torch.nn actually helps us. Okay, so say for example, if I want to compute convolution operation over an image. Okay, so I'm calling this con2d operation or function from this module. Okay, so this particular function is implemented using the functionalities from torch. Okay, so somebody have already implemented how to compute a convolution over an image. Okay, so if you don't want their implementation, or if you see some pitfalls in their implementation, either you can improvise it or you can implement on your own. So if you want to implement on your own, then torch module alone is sufficient. Okay, so you can, that I will demonstrate with a simple example. So that is what I wish to say. Okay, so this torch.nn contains almost 80% of the functionality required to build any kind of deep learning architecture. Okay, so as you can see from here, it contains a convolution layer and pooling layer which we want. Other than that, linear layer, dropout. Okay, so probably some loss functions. There are plenty of loss functions. So everything is there, and transformer layer, which is very recent, is also there. Okay, so and these modules will get updated quarterly. As I know, for every 3 months once, they keep on updating these modules with new functionalities. uh, you know every year there will be plenty of papers coming with new ideas. So all those ideas will be, if it is very vital and quite different, it will be incorporated into this framework. Okay, so now let us take a look into the architecture that we are going to implement. So this is our own architecture. We decided to use this architecture on CIFAR 10 dataset. Okay, so for various reasons, probably we can try this architecture on CIFAR 10 and see how it performs to the existing architectures. Okay, so what is the thing that you have to remember? So this is going to be my input side, which is an image, and this one is going to be first convolution layer. Okay, so I'm going to use 6 kernels in the first convolution layer. Still, we didn't decide about the spatial size of the kernel. And probably we can use 3 cross 3 kernels. Okay, and then we are using probably this is a max pooling layer because the dimension is reduced by factor of 2. And then I'm using second convolution layer. Okay, but now this time with 16 kernels. Okay, and remember, each side we are manually entering the expected output dimension. Okay, so by using that formula. So here again followed by max pooling layer, this 10 by 10 is reduced to 5 by 6. Then I simply stretch out this convolution, the kernels in this convolution into a single dimension vector. Okay, so which means it will contain 16 into 5 into 5 numbers. So we simply stretch this out. Okay, then this part is essentially artificial neural network or deep neural network. So it is a fully connected layer. So if you wish, we can use dropout in between these layers. But for the time being, we don't implement any sort of regularization techniques. We just try to implement this architecture in PyTorch and see how it performs. Okay. So what are all the things we need to know? So we need to know how to carry out this convolution operation. We need to know which activation function is suitable and which loss function is suitable and which optimization algorithm is suitable. Okay, so if you know all these things, that is enough. Okay, so we can simply directly implement this architecture into the using PyTorch functionalities. Okay. Now I will just give you a link for the IPython file. Okay, so I have just pasted a link in the chat box. So you click on this link and please download that file and then upload it into Colab. Upload it to the Colab. So if you have successfully uploaded that into Colab, you just type uploaded to Colab in chat box. Okay. So now you will see a similar notebook in the Colab. So however, I am running this Colab in my local system. Sorry, this notebook in my local system. So it will be without any issues. It should be get executed in the Colab as well. So if you face any issues, you just let me know it. Okay. So let us take a look into this core PyTorch module, that is torch alone, and also let us take a look into whether GPU is available, all these things. So if you execute this cell, so whether GPU is available, yes, available. So also it shows you the configuration of this particular GPU with 32 GB memory. So you should get an output accordingly based on the Colab configuration. You might see 15 GB memory, something like that. So the first step, let us try to understand. Even though you already know it, probably if it is already covered, again for the sake of completeness, let me cover this as well. Okay. So the first thing is everything is a tensor, whether it is a single number or a vector or a matrix or a three-dimensional cube, whatever it may be. So in PyTorch, everything is considered as a tensor. Okay, single dimensional, 1D, all these things. So if you want to create a tensor, you have to call this functionality torch.tensor. Okay, so we will use this square bracket like we do in NumPy. So I think let me share the whiteboard. Okay. Okay, I hope you are able to see the presentation. So the extremely important thing, I would say, is to understand how to create these kind of tensors. Okay, so you can call this torch.tensor to create any dimensional tensor, whether it is one dimensional, 2, 3, or 4 or 5, doesn't matter. Okay, so we use a square bracket to add an axis to add an axis or add a dimension whatsoever name to my tensor. Okay, so if I have only one square bracket, it is actually 0 dimension, and if I want to create a tensor within this, okay, so I am using again one more square brackets, open bracket and close bracket, and then I'm putting one more open bracket and close bracket. Okay, so my 0th dimension contains two elements, so which is again a square brackets alone, which means it is an additional axis. Okay, so my dimension 0 contains two elements, sometimes they call it as an axis. Then what about the dimension 1? Okay, so if we move on to the dimension 1, say for example if we put 1, 2, 3 here, then 4, 5, 6 here, then dimension 1 contains 3 elements. Okay, so like this you can keep on putting square brackets by nesting it, right? So again I can create these inside this. Okay, so we can keep on creating manually, or we can add more access by using these square brackets, nesting the square brackets inside. Okay, oftentimes we won't do this, but just to understand what this dimension means and what is this axis means, we are going to do this manually. Okay, because once if you have an understanding about this, then you can deal with any type of data with any dimension. Okay, there won't be any obstacle. So here what we are doing is you just pay attention on the square brackets. So I have one outer square bracket and then two inner square brackets, which means the outer square bracket is the 0th dimension, contains two elements in it, and then inside it we have three more elements. Okay, so that is the first dimension. So inside that we have three more elements. Okay, so now we have just created a sort of matrix. Okay, so you can execute this. Then if you just print out this x dot end in, it says the dimension is 2. Okay, say for example you imagine x is now an image. Okay, image loaded from probably your local disk. So in such a case, if you put x dot end in, and if it prints 2 means there are two dimension, meaning that probably that could be an grayscale image. Okay, and what is the dimension? I mean, how many elements are there in the each dimension? That is what given by this x dot shape. Okay, so it says that the dimension 0 contains two elements. Okay, which one? This square bracket and then this square bracket, inner square brackets. And then dimension 1 contains three elements, which is these three numbers 1, 1, 1, 1, and then 2, 2, 2, 1. Okay, so if it is a square image, you will have 3, 3, all these things. Okay, and then oftentimes since we are just entering 1, 1, 1, by default, torch.tensor the data type of those tensor will be long, but we want to restrict the data type to float because we are going to carry a lot of multiplication, division, all these things. So we restrict the data type to float 32. So I'm just assigning it here, and since GPU is available, I'm changing the device where the computation must take place to CUDA. Okay. So here, without executing this code, yeah, so the same code, now I have just changed the data type. So the data type will be now float 32. Okay, so by default, even though I have just typed 111, which is an integer, but since I set the data type to float, so it is a float. You always follow this. Okay, you ensure that your data type is float 32. So here is a three-dimensional tensor. So it looks like quite complicated, but if you decompose this into outer square bracket and then inner square bracket and inner square bracket, you can see what the dimension is and how many elements are there in each dimension. Okay, so here you can see this is the outer square bracket. Okay, then so parallelly, I hope you parallelly do this in Colab. So in the outer square bracket, I'm looking at the other square bracket, inner square bracket. So here I'm seeing 1, here I'm seeing the second one, and then third one, okay, which means the zeroth dimension contains 3 elements, okay, and then within that again I have inner square brackets 3, I mean 1 and then 2. So the same is true, 1 and then 2. So you can see it is being highlighted, right? So the inner dimension contains 2 elements, and then within that again it contains 2 elements, okay. So if you now print x dot ndim, it will display 3, 2, 2, okay, meaning that the zeroth dimension contains 3 elements, and then for each element in the zeroth dimension there will be a first dimension which contains 2 elements. So for each element in the first dimension it will contain 2 elements, okay. So that is the meaning of this. So if you want to see that, you can simply print x dot shape. Okay, so it is 3, 2, 2. So if you think of this as an image which is really bigger, okay, so it will also contains 3, but if it is an image, the size will be 100 comma 100. Okay, so this format is channel first format. So image representation usually, if you want to represent an image, usually people write 100 cross 3, where this 3 actually represents channels, where the channel is coming at the last position, but oftentimes this is also acceptable one, okay. So now the channel is first, okay. So if you want to make use of existing architecture, you should know what sort of image they passed to their architecture. I mean, they used it to train their architecture, whether the channel first or channel last. So it doesn't matter if you come to know it is a channel first, then you can change it by using reshaping command. So once if you create a vector, then next step is to access an elements or tensor. The next step is to access an element in a tensor, okay. So here I am accessing the zeroth element in the zeroth dimension, okay, which in my zeroth dimension contains 3 elements. So I am just accessing the zeroth element and I am looking at this shape. Here I am accessing this 0 means that I am accessing the first channel out of 3, and then this 0 means that I am accessing the first element in the first channel, okay, so which contains again a matrix, okay. So if you execute this, you will get single number. You can see that this is an element residing at the first element in 0th dimension, okay. Again I'm accessing the first element in the first dimension, which is 1, 1, 1. And if you don't get this straight away, okay, so of course we need to practice a lot, even though I orally try to explain all these things with minimal words, but it might still confuse you a lot, because when I learned all these things during the first time, it is very difficult for me to grasp all these things. But once if you keep working on by creating your own example or by taking an example from other resources, then you will understand all these things. This is an extremely important one. So once if you are able to create a tensor, and if you are able to access an element from a tensor, then you have gained almost 30% of the skill required to develop any deep learning architecture, because it is going to be the same: create, access, manipulate, okay. So maybe you can note it down if you really want to. The entire algorithm, deep learning algorithm, is all about create and then access and then manipulate or modify, and then probably we not store it, okay. So these 3 cycles are connected together: create, access, manipulate means it's a kind of you do optimization, change the values, okay, and then probably you can restore it, okay. It's a kind of going to be a cycle. So here what this particular cell is doing is we are simply uh, doing one convolution operation, okay. So here I have 2 tensors, and this I'm calling this an image variable, which is a small patch in the entire image, okay. You can think of like that. Then I am defining my own kernel. So these kernels, as you know, all of them are 111 that we have just discussed in the classroom. Of course 1 by 9 is there, but let it be 111. So this is image is of size 3 cross 3, kernel is of size 3 cross 3. And then what we do is we just make a dot product between these two. We simply multiply the kernel with the image element wise, right? So now these two are tensors. So you can simply multiply them by using this torch.mul. Remember, I don't use any other modules. I'm just using this torch module. Okay, so torch.mul. So it will multiply and it will store. So if you multiply two matrix element wise, the result is also a matrix. Okay. So what we do is next we compute. Um, so I should. This is not necessary. So this is a okay. So this is a matrix. Then I have to sum it up. Okay, that is the meaning of dot product, right? So you multiply the element wise and sum it up. So this is actually a linear operation. Then we have to pass through some activation function. So this dot clamp act as a ReLU activation function. Okay, so you can use torch.max as well, but clamp is also act as a ReLU activation. Okay, so if you just execute this, you can see this is an element wise multiplication, and after this linear product or a dot product, my answer is -1. Okay, so if you pass this -1 through the ReLU activation function, it will only and I hope so. This is the ReLU activation. Okay. So it's something like this. So if my answer is positive, okay, it will keep that answer. I mean the result as it is without doing anything. So whatever the number is an input, that number will be an output. Okay, so it is simply mapped like that. But if my result is negative, okay, so it simply whatever the negative number, it will simply map it to 0. Okay, that is what this relay activation function does. So that is what the output is here as well. Okay, so since the answer is negative, the output is 0. So now you have created a convolution operation and you pass it. Of course, you can add bias as well. You just pass it through an activation function. Okay, now you have to repeat this process. My kernel is going to be the same. Okay, now you have to repeat this process by moving this kernel over an image. Okay, so for that you have to simply add two more for loops. Okay, you can use for loops and then you can move that window over an image. Okay, so actually the con2d function is implemented like this only. So we will use con2d function, but behind the screen it is actually doing all these things. Okay, and suppose if I want to use sigmoid layer, I can do that here as well. So here we have just implemented the sigmoid function. Okay, again using this torch module, no other modules. So if you implement this, you are getting some output. This is our own implementation with 3 lines of code. Now we are using torch.nn module helps us already implemented the same code for this sigmoid function. Okay, now you can use this sigmoid function as well for the same input. You can see the outputs are same, right? 0.7311. This is also 0. All the elements values are same. Okay, so now you have two choices. You can implement anything from the scratch, or you can make use of the uh, already implemented functionalities available in different modules, torch.nn or torch.init. Okay, so it all depends on you only. So if you implement it from the scratch, you can see what is going on if it is required. If you don't implement from the scratch, then you don't have that flexibility. Okay, so now let us look into how to implement this our own architecture, Cornet architecture using Torch. Okay, so first I'm importing this Torch vision because this Torch vision contains the data set as well as the transformation required for this data set. Okay, and then as I told you already, we use this module torch.utils.data for many data processing tasks. Okay, so loading data from the folder. So for because it acts as a sort of generator function in Python. Okay, and then these two are just to plot and see the or if you want to visualize what is going on there, so you can use this matplotlib. So let us import this. Okay, so now I want to see what are all the data sets available from this Torch Vision. Okay, so Torch Vision is a computer vision application module. So you can see all the pre-built data sets. Okay, so you can see it comes with CIFAR 10, CIFAR 100, and Caltech 101, and even sometimes the very basic MNIST. And even you can, if you have an access to GPU, okay. So if you have an access to GPUs, powerful GPUs, even you can train your architecture for ImageNet as well. Okay. So you need to, they are benchmarking data sets. So even if you want to use your own data set for some other application, you can prepare the data set and use this module torch.utils.data. Okay. So oftentimes we need to carry out some sort of normalization process. Then we remember these data sets when you, even though I'm going to load the CIFAR 10 data set, which is actually a NumPy array or some other format, say probably pickle format. Okay, but here all the operations are taking place with the data type torch.tensor. Okay, so first I have to convert the data type. So for that, for each sample, I have to convert that into a tensor. So these two tensor will take care of that one, and then I should also normalize all the three channels in the image. Okay, so the image is going to be color image. So this is the value for mean and variance for all the channels. So like this, still you can do a lot of pre-processing like cropping and rotation. So whatever the pre-processing step you want to apply on each samples in a data set, you can use this transform.compose function. Okay, so now after defining this, we are just going to load the data set and I'm going to load this and store it in locally. And then we are setting trains equal to true, which means you load the training data set, and then downloads equal to true, which means you download it to my local system. If it doesn't exist, it will download and store it in my local system. Okay, the same thing is we are repeating the same code for test data set. Okay, so it is already downloaded in my system. Therefore, it says it already exists. So you can see here I have a data folder here. You can see these two things are downloaded and stored here. Okay, so it is actually tar.gs is what gets downloaded when you execute that code. Okay, it's still in a compressed format. Okay, so like this, if you execute that, it will be downloaded to the Colab's local memory location. Okay, so are you able to follow this without any error? I hope so. Okay, so now if I want to look at the number of classes and what is the name of the class, all these things, we can use these functionalities. Okay, so you can see there are 10 classes with these names, and also you can see this is a training set, right? So there are 50,000 images for training, and this is the dimension of each sample. So each of them are size 32 cross 32 cross 3. Okay, so this data loader function here is actually a generator. Okay, so I'm not sure whether you already know about the Python generators and iterators. For that, let me give you a simple example. So why we are using generator? Why don't we use this data as it is meaning that, as I told you already, if you load all the datas uh, locally to your memory, it will occupy a lot of memory. I want to load data one by one. So the generator function actually does this job. Okay, so you can create a generator function in Python by using this function definition and as well as yield. Okay, so let us ignore that for the moment because that is not necessary. So you can just learn it online. So now I'm using this generator function. Okay, so this data loader is a generator function. Then it will look into the train set. Okay, my train set actually contains 50,000 images, right? But whenever I use this data loader, whenever I call this generator function data loader, then it will only return 4 images out of this 15 images. Okay, and then I am also set shuffles equal to true. So meaning that so we have 50,000 images named from 1, 2, 3 all the way up to. So this is just an index of an image. So my data loader act as a generator, okay, which interact with this folder and also interact with my coding part. Okay. So whenever I call this data loader using some callback function, whenever I call this data loader and setting shuffles equal to true, it will randomly pick 4 images. Since my batch size equal to 4, it will randomly pick 4 images from some location, and it will return those 4 images to my called function, right? And also it ensures that during the next call, these 4 indexes will not be used. So for each call, the indexes are going to be new and random. Okay. So that is why we can eliminate loading all the images into the local memory. Okay. So we are repeating the same for test set as well. Okay. So now my train loader is a generator and test loader is a generator. So whenever I call this train loader and test loader, it will return 4 images out of the 50,000 images and 10,000 images respectively. Okay. So I am just doing that now. Okay. So let us execute this line. So I want to see a few images from my data set. So for that, again, I'm calling this train loader function with a special function iterator. Okay, so iter. So this is a function that can be used. So whenever this iter function IET or iter function is called on a generator, it will take 4 samples. So if you want the next 4 samples, then you have to call this again. Okay, so since I just want to see uh, any random 4 samples, I am just calling this one, and xtrain will contain 4 samples. Okay, then of course this next will load the image and label. Okay, and then these lines are just to plot an image. Okay, so using matplotlib. So I am just loading 4 images randomly from my training data set. So here you can see it is a horse. It is not clear because the size is very low, right? 32 cross 32 is extremely low. So even though we can accept this is a horse, it is very difficult to recognize this is a dog. This is extremely difficult to recognize it is a frog. Probably it is easier for us to recognize this is a car, okay? Because of the row resolution. So if I execute this cell again, now I will get a different images, okay, right? Because now that index will not be accessed again. So each time you execute this cell, you will get a different subset 4 images from out of these 50,000 images until all the 50,000 images are displayed. Here you can see now a new class bird. Okay, of course we know that it is recognizable for us, but this one is, even though it says it is a dog, it is quite difficult to recognize. Okay, so now I have some idea about the resolution, and if I have also ensured that the data sets are properly loaded with the correct label. Okay, because while implementing this supervised learning algorithms, any sort of supervised learning algorithms, if we make any mistakes in labeling, okay, so if you make any simple mistakes in labeling, we never know that the poor performance of a deep learning architecture is due to this labeling issue. Okay, we made a mistake in a label. Now we are training a deep learning architecture using those labels. Now the performance of the deep learning architecture is enormously low, but we try out with a different architecture with a different loss function optimization function. But no matter what, the performance is going to be low. Okay, the reason is because there is an error in the labeling. So a thumb rule is that you have to spend almost 90% or even 80% of your time on ensuring on creating a proper data set with a proper label. You have to ensure everything. Okay, otherwise no matter what you do in the next 5 to 10 days, you will not get the proper results. Okay. Okay, now let us define the architecture. Now we are going to make use of only two modules. Okay, and then other than that, we will use one more module for optimization. And these modules are torch.nn and then torch.nn.function. So what these modules? So this module contains all the components pre-built into this module, which means I mean all the functionalities pre-built into this modules. Okay, I want to carry out the convolution operation, especially two-dimensional. So it is there in nn.module. So you can look at the documentation to refer to what are all the arguments that has to be passed to this module, right? So you can see it is in channels is an integer type, out channel is again an integer, and kernel size. Okay, and then these are all different types of annotation. Probably if you know Python depth, how to annotate, create an annotation for Python, you will see these kind of description in the documentation. Similarly, I am looking at the max pool layer and then linear layer. Okay, so these are all the three functionalities that we are going to use to create our architecture. So it is always better to look into the documentation before using a particular function. So if you already know it, there is no issue. But if it is new to it, then you have to look into the documentation. Okay. So usually, if you want to create an architecture, this is an Python OOPS concept. Okay, so if you already know what is class and what is inheritance, we are simply inheriting our base module. Okay, so to create any type of neural network, there are certain tasks which are common for all the neural network, like forward passing and then back propagating and then looking into the gradient. So this is common for any type of architecture, right? So all these operations are defined in this nn dot module. Okay, so whenever you create an architecture, you have to inherit it. Okay, so that is Python inheritance. So once if you inherit that, you can make use of all the functionalities defined in this base class, right? That is the purpose of inheritance. Next, I am defining the layers used in my architecture. Okay, so for that we are using this def init. So it is an Python constructor module, constructor method. Like in every OOPS language, there will be a constructor and destructor. So this is an Python constructor. Okay, so here again, let me display the architecture. So here is our architecture, right? So we are going to implement this architecture. So I am saying, so you just refer the documentation. What is the first thing? So it is an in channels, right? What is the how many channels are there in the input? So my input contains 3 channels. So we are just passing 3. Oftentimes, this is good practice. You type the argument name as it is, okay, so that it is readable for everyone. But it is not mandatory, but it's a good practice. Okay, so the second argument is out channels. Okay, which means what should be the output depth. So in this architecture, as we can see, we are going to use 6 kernels. Okay, I want to ensure the depth of the output is 6. So I am passing this 6, and what should be the spatial size of the kernel? Okay, so that is 5. So kernel size, the third argument. Okay, and then rest of the arguments are optional. So I need not to pass this stride. Optionally, it is set to 1. If I want to change this stride to 2, you can pass this argument. And then the padding, I don't want to add any padding, so padding by default is 0. So all the other arguments to this function are simply optional. So again, this is my first convolution layer. Next, I am defining the pooling layer, right? So max pool 2D. So again, the kernel size is 2, and then so you look at the documentation, kernel size is 2, and then stride is also 2. The second argument to this function is stride. Okay, so by default it is set to none, which means you have to pass what is the stride value. So we have passed stride value is equal to 2. Next, we are in second convolution layer. So the input depth is 6, and then we are going to use 16 kernels in the second convolution layer, again with the same kernel size. Finally, I have to use the max pooling for the second convolution layer, but since I have already defined the max pooling above, I am going to use the same kernel size and the same stride size. I need not to define it again. I can make use of the same this n and max pool during the forward pass. Okay, so after that we simply flatten out this one, and then we pass this 1 cross 400, right? So 16 into 5 into 5 is actually 400. Then in the artificial neural network, the first hidden layer contains 120 neurons, and then second hidden layer contains 84 neurons, and the third hidden layer contains 10 neurons. I mean the output layer. That is going to be my output layer, right? Which contains 10 neurons because the number of classes are 10. So this is a constructor class. Okay, so if you don't know the OOPS concept, it's all right. But if you want to make a research in deep learning domain, you better learn Python to the depth. Okay, especially the OOPS concept and this generator and iterator functions. Okay. So once if I create an architecture, the next step is I have to do forward pass. So for forward pass, we have to take an input X, only the input X, in terms of batch size or a single input, it doesn't matter. Okay. Then first I have to do carry out this convolution operation, then I have to pass this through ReLU activation, and then I have to do this pooling operation. So you recall that we are calling self.pool, and then self.con1. So actually this calls this particular one, self.con1 is actually nn.con2d. Okay, so this actually what to say uh, helps others to read your code quickly. Okay, so this class implementation, you might have implemented all these convolutional operation without using this class function. Okay, without creating an object called net. But there are reasons why we go for this approach. Okay, suppose if you want to validate 10 to 15 networks parallelly. Okay, with the different, the same architecture but with a different loss function, with a different optimization function, with a different activation function. You want to experiment that. Now you have an access to parallel computing. So in such a case, you can use this net module. Then you can create 10 different architecture with 10 different activation, all these things, and then you can parallelly compute. You can parallelly measure the performance. Okay,
Sir, Arun Prakash, sir.
ma'am.
Your voice is breaking, sir.
Ma'am, is that the case for all? Okay, ma'am, is this okay now?
Now it is okay, sir. It is audible.
Okay, ma'am.
Before that, it is.
Okay, okay, ma'am. Okay, so there are reasons you get used to it because creating architecture in this way have many advantages than simply creating the architecture just using those functionalities. Okay, so now as usual, actually Keras does this at the behind the screen. Okay, in Keras we will simply call model dot sequential. So here we are simply assigning it net to this model. Okay, so what this code does is it will move the model to GPU, and then printing this model will print the architecture itself. So I am executing the above cell. I think I didn't import. First let us execute this, then let me execute this cell. Now I have created the architecture. Let us see whether, so you can see the details here, right? So this architecture, all these things, what is the input kernel, the input depth, output depth, kernel size, everything is printed nicely, including the number of features, 400. Okay, all these things. So now we have just created the skeleton, right? We have just created the architecture. We didn't initialize the architecture with random values. We didn't define the loss function. So we need to, the second step is once after creating this skeleton, next you have to define the suitable loss function. So this is a classification task. So the cross entropy loss is the suitable loss function for this classification task. And then also you have to define what type of optimization algorithm we are going to use. So here we are using momentum based SGD. So it's a kind of optimization algorithm which converges quickly. Okay, so which means you need not to wait for longer to see how your model actually performs. Okay, so we are just importing this module optim, and then we are setting all these things, loss and optimization. Okay, so now everything is ready. So what is our next step? Now we have, okay, so I have prepared the data set. Next, now we have created the architecture. Okay, we have created the architecture. Now with the proper loss and then optimization, everything. Okay, so now I have to load an image from my data set batch wise, and then look at the loss function, and then use an optimizer, okay, which is already defined, fine tune the parameters in the architecture, and then again repeat this process. Once if you fine tune, you take another set of 4 images. Again you pass the entire training set over this architecture, you measure the loss. So this cycle is going to repeat it. Okay, so which means we are getting into this looping. So we use this for loop. Okay, probably you can use while loop as well, suppose if you have any conditions to break. Okay, so again for the sake of illustration, I am setting this range to 2. This is an epoch. And again, let me tell you one topic and let me give you a break. Okay, so now I have these 50,000 images and batch size of 4. Okay, so now I have two things, two parameters, iterations and epochs. So what is iteration? So during each iteration, I take only 4 images out of these 50,000 images and pass it through the network and measure the loss. So how many iterations will be there? Since there are 50,000 images, and dividing this by 4 probably will give you some answer. 1, 2, something like this. Okay, around some 12,000 something. Okay, there will be some 12,000 iterations for each epoch. Okay, let me calculate that. $3,000 okay, 12,500, right? So if I set my batch is equal to 4, then after this 12,500 iteration, one epoch is over. Okay, so I will average out all the loss functions. Okay, then during the next epoch, again I will take the entire training set. Okay, so the key takeaway is during each epoch, you pass the entire training set, but during each iteration, you just take the only some images set by this batch size value. Okay, so now if I set 2 epochs, now I trained my model 2 times with complete 50,000 images. Okay, it will definitely going to take some time. So that is why I set this to 2. But you can run the model for any number of epochs as long as it converges to a minimum loss value. So here I am setting 2 variables, running loss, because we want this is a loss measured during each iteration, but I want the loss after passing all the 50,000 images. So we set this as running loss and running accuracy. Then train loader is an generator function which takes only 4 during each call. It will take only 4 images out of the 50,000. So I will call this around some 12,500 times, right? So and the rest of the things. So this data will carry now images and labels. I think I need not to explain a lot about this. You can just go through the code. So what we are doing is here, we are moving this input and labels to the GPU. Okay, because my architecture is now in GPU, therefore the calculation must also be carried out in the GPU. Okay, so therefore we are moving this to GPU. Now we are setting this gradients to 0. So because I don't need the gradients, because during the back propagation part, okay, the forward propagation, we take an image and pass it through the architecture, it will compute the loss. During the back propagation, again I will calculate the gradient for each node in the entire architecture. Then we store those gradient if required. Okay, usually if you want to visualize how the gradient is changing over iteration or over a path, you would like to store those gradients. But this time I don't need to store all those gradients. So I'm just, because if you store all those gradients, it simply occupies the memory space unnecessarily. So we set this to 0 grad. Okay. So the important thing happens here. So my model is now, and just for comparison, so my model, the variable model now holds my entire architecture, right? So I am just passing an input to this model. Okay, now my inputs contains 4 images. Now I am passing this to model. Then the model will give an output prediction for these 4 images. Then I compare this output prediction with the ground truth. Then this loss will compute and pass this to this loss function. Then it will compute what is the loss, cross entropy loss. Then I am calling this backward function. Okay, so once if I call the backward function, then it will start computing gradients. Okay, so if you want to compute the gradient for one iteration, I'm calling this dot step. Okay, so we are doing this everything manually, which means I can control how the gradient should be computed. Okay, so if you really want to implement your own optimization algorithm, or if you really want to see how the, as I told you previously, how the gradient is changing for each iteration, then you can call this, you can control this optimizer dot step. However, we don't want to do all these things. So what we are doing here is we are simply computing running loss, which means we are computing loss for all the 12,500 iterations, and we store it here. But I want to display the loss I want to display the loss only after 2000 iteration, because if I execute this, I don't want to see all the outputs. Okay, I want to see the output, the loss function and the loss value and accuracy value only after 2000 iterations. So we are doing this here. Okay, so I am dividing this by 2000 because I want to compute the total loss, not the running loss. Again, I want to compute the total accuracy, not the running accuracy. So this is the simplest setup. We have set everything correct. Now let us, if we execute this, like you see in Keras, you will see the same thing in Keras, or in high level API, you will see the same thing here as well. Okay, now only 2000 iterations are over, 4000 iterations over. And also you can see the loss is consistently decreasing, accuracy is consistently increasing. Okay. Now one epoch is over. Now we are in second epoch, but we are repeating the same iterations. Okay. Again, it is computing the same thing. You can see that loss is still consistently decreasing. Now two epochs are over. Okay, so you can see the loss is now 1.338. The accuracy is now 0.529. Okay, so even the biggest or the deeper CNN have produced 93 or 95 point something accuracy for this data set. Okay, but the simplest architecture that we have developed, that we have created now, is producing good accuracy only. Okay, it is not that much bad because even with the two epochs, the accuracy now is at 50, 52.9%. Okay, so if you run it for few more epochs, you can see the loss and accuracy keep on. I mean, the losses keep on decreasing and the accuracy will keep on increasing. Probably after few more epochs, you may see the other way around. The loss might also increase, which means our model is actually overfitting to the training data. Okay, and also you can split this training test into one more. Sorry, split this training data set into one more thing, that is validation set, uh, which might be helpful to avoid this sort of underfitting and overfitting problem. Okay, you can use that to recognize whether it is underfitting or overfitting. Okay, so now I have trained the model. Then if I set this to evaluation mode, then I can use this to evaluate the model for the test set. Okay, now evaluating over the test set takes only one epoch. You need not to do this iteration. Okay, however, I'm load since I cannot load all these test samples into the memory. Still, I'm using enumerating over the entire test set 4 by 4. Okay, so that I may not crash the system. But after this, I'm just printing the final accuracy. As you can see, the accuracy is 54. Testing accuracy is 54.56, and this is actually computed on CUDA. I mean, sorry, the NVIDIA GPU, Tesla GPU. Okay, so whether this model underfits or overfits, no, because the training accuracy is 52.9 and the testing accuracy is 54.5. So far it doesn't either overfit or underfit. But if you run it for a few more epochs, probably you come to know whether it underfits or overfits. Okay. So with this, we may take some 10 minutes of break. And then if you have any doubts, you can ask me now and then come back after the break. So you parallelly execute it in the Colab and try to understand the codes. Okay, I hope there is no doubts. Okay, let us take a break for 10 minutes. Okay. So now what we are going to do is, so now we have trained our own model from the scratch. By the way, even though accuracy is 50%, so this is how a general training procedure, I mean, training in general architecture happens, right? So if you have an access to large uh, computational power, you can train any model, AlexNet or VGGNet, or even a very depth model on it. Uh, but you have to follow the same procedure. The general pipeline is going to remain same. So now let us take a look into how to make use of these kind of trained models. Okay, suppose if you are a researcher and you build some architecture that is suitable for some application and you want to share it with others. Probably say you are working on some medical image segmentation or optical character recognition for some language. You train a model, you have an access to a GPU, train a model, and the performance of that model is superior to the existing system. So you want to you want to give away that model to all others, or in other words, you just want to open source your model. Okay, so now everybody have an access to your model. Like that, same thing is true for bigger models like AlexNet and VGGNet, all these things. Okay, so researchers in Google and Facebook and in other academia train their models and then they simply open source it for other applications. Okay, so we call such models as pre-trained models. Okay, so if I want to make use of AlexNet for my application, which is already trained by some other researchers using their computational resources, then I can make use of their model. Then we call that as pre-trained, which means the weights are freezed, the parameter values are fixed. Okay, so this is what you see here. So now, again, let me import all these things. Now what I want to do is I want to load an AlexNet or ResNet or whatever. Okay, so I'm loading all the required packages, but the additional command or the module that we are going to use is again we are importing a set of pre-trained models from this Torch Vision module. Okay, so for that we are using this function from Torch Vision import models. So I'm using others these kind of packages so that you can also render this in Google Colab without any glitch. Okay, I'm loading an image from some website directly into my notebook. For that we use this web URL requests. So I can see what are all the models available, pre-trained models available in PyTorch, and then there are plenty of pre-trained models tailored for different applications. So here I just would like to use AlexNet, and while calling this AlexNet, I am setting pre-trained is equal to true. Okay, what does that mean? There are two options now. Either you can just load the entire architecture without any weights. Okay, so you can again train the model from the scratch like we did earlier. Okay, so instead of creating the architecture manually by typing all the by passing all the arguments, because the architecture is really big, it takes a lot of time. But if I set this argument to false, what really happens is that only the architecture will be loaded, not the weights of the architecture or parameter of the architecture. If I set this to true, then the architecture along with the trained parameters will be loaded into this variable AlexNet. Okay, so the next immediate step is researchers might have trained the model by pre-processing their images, right? So I have some data set. So earlier we pre-processed in a data set. We just carried out one pre-processing step, that is normalization, right? But the AlexNet is actually trained on ImageNet, but the researchers have carried out a n number of pre-training tasks or pre-processing tasks. So whatever the image says, you resize it to 256 because the ImageNet is composed of millions of images of different sizes. So first you have to resize that, and then you do the center cropping, And as usual, this is now we are doing the inference with PyTorch. So you have to convert that into torch tensor. So use this to two tensor functionality. And then we do this normalization, mean normalization and standard deviation normalization for each channel in the input image. So now let me execute this. Now the AlexNet is loaded into my local system. Okay, the entire architecture is now here. So if I want to look into the architecture details like we did earlier for our model, we simply print, we passed an argument model. Here we are passing this, we are just printing this variable AlexNet which contains the details of the architecture. So you can see here what is, there is a convolution layer with input. Of course, the first convolution layer, the input is, the input channel is 3 because it is an RGB image. The first convolution layer uses 64 kernels, and the first kernel size is, all of them are 11 cross 11, stride is 4 cross 4. Okay, so you can go through all these details of the architecture by simply using this print command. Now, since it is already trained and only the trained model is loaded now, I want to use this trained model. Okay, so for that, what we do is I'm just loading an image from an internet. Okay, from some web address. So I'm just loading and displaying it here. As you can see, it is an dog image. The size is 1000 cross 800 cross 1000. But remember that I cannot pass this image to AlexNet as it is. AlexNet requires the size of 224 cross 224, which means I need to resize it, and then I have to normalize it, and then I have to convert this vector into a PyTorch tensor. So I do all these things by using this transform function. Okay, so we just define this transform, right? So we just define these transforms and what are all the operation has to be carried over this image. So now it is, once this line gets executed, okay, once if this gets executed, then this image will be center cropped and converted into size of 24 plus 224, all these things. Okay. So now I set the architecture into evaluation mode. So let me print this. So now it has made a prediction. Okay, so the number is 1,1000. The reason is there are 1000 classes. So it has just returned a number. That is the probability value for all the classes. So next we do some task where I would like to load the class labels, right? I want to know the name of each classes. So we are just doing that. So there are 1000 classes. As you can see, these are all the class names, right? So now let us pass this image. Sorry, we have already passed this image. Let us print the predicted class with its class name. Okay, so now I just going to print the class name. So the input image is actually a golden retriever, which is a breed of a dog. Okay, so now the confidence score is 75.23, which means this particular class is being given with the highest probability. Okay, so the 75.23 is actually the confidence score. Now, like this, you can pass the different images to this architecture by loading different. Now, let us do this for this one. So this is another kind of dog. Now, let me pass this dog to the architecture. So, what it says. So of course you can do another patching work, like you can you can show the image and type the predicted class on the image using OpenCV module. So it is not a big thing at all. Okay, so displaying an image and showing a name of the image on it. But here you can see the prediction is now German Shepherd, the exact prediction, and also you look at the confidence score. It is 98.87. It is highly confident about its prediction. Okay, so you can change these images, but I would like to change. I would like to test the final image. So now you can see this image is a golden fish. So let us pass this through FlexNet. Now let us see what it says. It says it is a jellyfish, right? With a confidence of 78.7. Okay, so you recall that the performance of AlexNet on ImageNet dataset is uh, not good. Even though that is the breakthrough, then people have come up with a different architecture to improve the performance. So now we are loading a RISC-net architecture. Okay, then I'm doing the same thing. Now let us see, I have just compiled all the lines into a single cell. Now we are loading an image, transform an image, and then we pass this through a ResNet architecture, and then we make a prediction. So I'm using the softmax to give the probability, uh, I mean the probability score for each class. Okay, and then you multiply this by 100 just to give the confidence score. So the same image now passed through an ResNet architecture. Now the prediction from the ResNet architecture is it says it is a goldfish, but the important thing is it says the confidential score is now 99.93. It is very much confident about its prediction. Okay, so this is about ResNet 101 layer. You can see the entire inference takes place with only 4 lines of code. It is always the case. Okay, training the model takes some 30 to 40 lines of code, but testing the model will happen only in 2 lines of code. Okay, sorry, not testing, inferring the model happens always in with just 2 lines of code. Okay, so now what we did is we simply loaded the pre-trained model and then we used it for some sort of application. Okay, so we didn't train the model from the scratch, we made use of it. Like that, there is something called as model zoo, where you can look for pre-trained models for specific applications. If you want to uh, use a model for object detection, it is there. If you want to use the model for segmentation, it is there. All of them are pre-trained. So if your only objective is to use them for some application, you can use it. But if you want to use those models for your application, say for example, um, this AlexNet is actually trained on an ImageNet dataset which contains 1,000 classes. Now, what I feel is that I would like to use this AlexNet. I want to use the same architecture of the AlexNet, but now I would like to use this for 2 classes. Okay, so initially the AlexNet is actually trained on 1,000 classes, but now I would like to use this for only 2 classes, which means I have to modify the architecture only final layer of the architecture. That is sufficient. Okay, so what we can do is we can simply remove the final layers in the AlexNet, and then we can modify the layer with 2 neurons to have 2 class prediction. Okay, so that we call it as a transfer learning. So the model is actually trained on some other data set, but now I would like to use that model for my data set. So with this process is called as transfer learning. So I am doing it here as usual. Now I have my data set stored locally in my own system. Okay, so I'm not loading a data set that is already comes with this PyTorch. Now I have a data set in my local system. So I have stored the data set as we discussed earlier in the first session. Okay, so we have just ensured that the structure of the folders are train and test, and within this train it will contain all the folders with class names, and again within this test folder it will contain number of folders with the proper class name. Okay, so now I don't want to pass image as it is. I want to carry a lot of pre-processing uh, pre-processing steps on every sample in my image. So we are defining this transform dot compose. Okay, so what are all the pre-processing tasks? I want to resize an image to 256 cross 256, and then I want to scale it. Okay, and then I want to rotate it slightly, and then we might flip it. So we can do all these things if we have very few data sets. Okay, so it's called of data augmentation. Okay, if you are running, if you have only a few data sets or few data samples for each class, then you can augment it during the training process. Okay, same thing we do in the testing process except few process. So now let me execute this. Again, I'm first thing I'm setting the training and testing directory. Okay, you can see my training folder resides locally. So this path actually says the folder is in my local system. So you can access this from the local directory. Okay, so I am passing this to image folder. So this is an again coming from image folder is a module residing at datasets. Okay, so which means my dataset are still an images kept it in my folder. So I want to load these images one by one. So we are using this image folder functionality. So I'm just pausing the directory, and during while accessing an image from those folders, you also do these transformations that we have defined in the previous cell. Okay. What happened? Oh, I think I have deleted that folder. Let me look into that. What is the folder name? So is that. So the folder name is not data, it's conflict. Okay. Now let me. So again, we look, we are setting batch size equal to 8, which means even though there are 10,000 images, it will load only 8 images out of this 10,000, and number of classes is 2. Okay. So this is just a demo. Again, you recall we have already used this generator function. Okay, so I don't want to load all the images. I want to load only subset of images from the entire training set. So we are using this data loader. Again, I am setting batch is equal to 8 and shuffle is equal to 2. So we are following the same set of things. So the only difference is now I am not creating the architecture from the scratch. This is not my architecture. So I am making use of the existing architecture. Okay, now we are making use of the RESTnet architecture. Okay, so now I am setting this pre-trained equal to true because I want to load not only the architecture, also the trained weights of that architecture. Okay, so now I'm just loading this, and let us see how many parameters are there in the architecture. Okay. So it is around some 25 million parameters. Okay, so 25 into 10 to the power 6. So it is 25 million parameters. So now, since I'm going to use this architecture, and I also want to add few layers. Okay, so before doing so, I want to set this required gradient is equal to false, meaning that all the trainable parameters, all the parameters will be freezed. Okay, meaning is, oh, how can I explain? So let me explain with. Let me try to explain this with a whiteboard. So what is transfer learning first of all? So let us assume we have a model, a trained model. So each trained model will contain some parameters. Okay, so suppose if we say the trained model contains only two kernels. Okay, the kernel 1 with 9 parameters and the kernel 2 with 9 parameters. Okay, so these are all the only parameters. So totally only 18 parameters are there in a model. So what I want to do now is I want to load this trained model, but I want to freeze these parameters. Okay, so I am going to use this trained model. Let us say this model is actually trained on ImageNet. Okay, but I am going to train the same model on my own dataset. Okay, I am going to use my own dataset. So in such a case, what I would like to do is I want to keep a few training parameters freezed. Okay, so here I have two kernels, so I want to keep the parameters which are fine-tuned for ImageNet. Okay, so these are the parameter values, so I want to freeze it. Okay, but I want to make this particular kernel to learn for my dataset. Okay, so essentially what it does is every CNN layer, con layer, then the output from the con layer will be passed to fully connected layer, right? Then it will give an class prediction. So this is the general setting. Now what we are doing is we are setting this convolution layer as a future extractor. Okay. So which means I am freezing all the parameters in the convolution layer. Okay, so when I pass my own data set as an input, the parameters in this convolution layer will not get updated. Only parameters in the fully connected layer will get updated. Okay, so now this entire module will act as an future extractor, but we don't know what sort of future it is extracting. We have no idea, but it is simply reducing the dimension of an image into some simple sort of vectors. So now we pass this through some classifier. So it could be an ANN classifier or an SVM classifier. It doesn't matter. Now entire thing act as a future extractor. Okay. So now let us go back to the coding. Okay. So I set this to false. All the trainable parameter. Now the trainable parameter is 0. So what we are going to do now is we are going to modify the architecture of ResNet 50. Okay, I am not modifying every layer in the ResNet 50. I am just modifying only the fully connected layer. Okay, so I'm going to add these two linear layers to the ResNet 50. Okay, so I have just chopped off the final output layers in the ResNet 50. I mean, I removed it, and then we are adding two more layers to this ResNet 50. Okay, so that we can do with this function nn.sequential, all these things. So now you can see it contains actually 2048 learnable parameters. And you can see these layers are added at the end. So this is the layers that we have added now, and then we are going to only update weights in this layer. So all other layers above, all these layers are freezed. Okay, so which means all the parameters in this layer are freezed. So during the training process, the parameter in this layer will not get updated. Okay, so that is what I wish to convey here. So how many? Now I have modified the entire architecture. So now look into how many parameters are there. Now there are 5,25,000 learnable parameters are there. So we can check this with this function. So previously, the original architecture ResNet 50 had 25 million parameters, right? 25 into 10 to the power 6 parameters. Now the same architecture after the modification, it contains just 5 lakh 0.5 learnable 0.5 into 10 to the power 6 learnable parameters, which means I can train this architecture even though the architecture is very big in terms of number of convolution layer, all these things. Now since the learnable parameters are very low, around 0.5 into 10 to the power 6, so I can train this model quickly. Okay, so that is the purpose of transfer learning. So now let us move this model to CUDA, so I mean the GPU. So we are repeating the same thing again, like as we did earlier. We are defining the loss function, negative log likelihood loss function. Let us do that. So instead of SGD optimizer, we are using Adam optimizer. Okay. Now everything is now get repeated from the previous thing. Okay, so all the things you can look at here. We load an input. We set the gradients to 0. Now this time we pass this input to the ResNet 50. In the previous time we passed the input to our own model. We calculate the loss and then we compute the gradient, and then we just update the parameters. Okay. Every other thing is same as like in the previous code. Now I can execute this on my own data set. So now you can see the entire execution is keep going. Okay, so this accuracy, see, it actually fluctuates between 0.8 and 1 because I have used only very few training examples. Not even though there are 12,000 training examples, I have used only around some 200 or 250 training examples. So this is not the correct accuracy. This is just an accuracy for a particular iteration, not for the entire training set. Okay, so but again, for the sake of demonstration, I have just used this. So you have a code with you, so you can use this code for your study to understand deeper. Okay, and once if you understand all these things, then you can refer PyTorch documentation uh, or even PyTorch tutorials for your specific application. Okay, still we can do demonstration for medical image segmentation. Um, okay, let me just execute that cell and show you what is going on here. So here what I'm doing is that I am taking a model trained by somebody else on a blind segmentation, and I don't know how they trained it, but I want to use that model, so we can do that. So this torch.hub.load actually loads the model from the third party. Okay, so somebody out there who is not associated with official Facebook research team, but trained a model on their own GPU, then they can upload their model, and then you can access that model from using this module torch.hub.load. Okay, so now we have loaded the model trained by them, okay, by setting this pre-train is equal to true. Now I just would like to load a few set of examples from their GitHub repository. So I'm just loading that. Now let us display, I mean forward pass. Now this is a segmentation. My input is an image and output is also an image. So let us display the output. Execute and then let's display the output. So as you can see here, of course I have no idea which is what part of this brain is being segmented, but you can see the output is properly segmented. Okay, so this is simply a map. So one color is a background and another color represents the foreground. So if it is some sort of cancerous tissue, you can see that it is actually extracted all these colors correctly. Okay, so it is actually distributed, but it is the model is able to recognize all these colors properly and highlight it. So if you want to train a unit from the scratch, you can see that we are using the same concept. We are creating an object, we are importing the module called nn.module, which is a base class for any type of architecture. Okay, so even though they are using unit architecture, you can do that. You must import this nn.module to create this architecture. Okay, and of course the unit is composed of two parts, encoding and decoder parts. These are all pre-built function defined by the author. Okay, so they are creating this architecture like as we did earlier. Okay, but this is really quite a bigger architecture. So there are a lot of components, both encoder and decoder is there. Apart from that, there is one more functionality, that is what is that? Transposed convolution. Okay, so output should be an image. So I have to do a transposed convolution in order to upsample an image from the encoder. Okay, the encoder is a sort of classifier. You can think of like that. And then again, it contains only two forward pass. So it is for, so everything is similar. So once if you understand the fundamentals with a simple examples, okay, so you need not to go for complex examples because it will confuse you. But if you understand anything with a simple examples, you can extend the same to the complex examples. Okay, so the important thing is you must have a clear understanding with simple examples. So that is enough. Okay, and of course there are plenty of online materials are there, you can refer it to. And it is, deep learning is an evolving field. Something so called state of the art today will become obsoleted tomorrow. Okay, say for example, people have used LSTM in RNN quite oftenly. LSTM, GRU, all these things, memory components, but now they have shifted to transformers. Okay, so it is evolving very quickly, so you have to, if you are a researcher, actually you have to keep in phase with this evaluation. You have to read it on a daily basis. What is going on there? All these things. Okay. So with this, I'm closing this session. So if you have any doubts, you can. Sorry, I didn't share the code. Okay, I'm very sorry for that. Um, okay. Ma'am, I have pasted the code in the chat box, so you can download it. By the way, I just organized the code, so you can take these codes from the PyTorch tutorial, but you have to organize it. That's all, according to your own flow. Okay, if you have any doubts, you can ask me. If it is in object classification or object detection, I could answer those questions. Okay, otherwise we can wind up the session, ma'am.
Sir, participants having any doubt? Sir, sir, participants not having any doubts, sir.
Okay, ma'am. So the final words are, of course, we cannot cover everything. As you know, deep learning is a very big field, and it has been evolving for the past 10 years. So covering from the basics to the advanced is quite difficult. But you can get some exposure about this deep learning, just an overview, what is going on here, all these things from this FTP. And then the important thing is you should keep going. So you should keep practicing uh, till you become comfortable with all these things. Okay, and thank you so much for your patient listening. Ma'am, thank you so much.
Thank you, sir. On behalf of participants, I thank Arun Prakash, Department of ECE, KEC, for providing the essential knowledge to perform object detections. Sir, you have demonstrated the DL models using PyTorch in detailed manner. You have clarified the participants' doubts also. Thank you, sir. And also, I would like to thank all the participants. Participants, kindly fill the feedback link, which is given in the chat window. So tomorrow's session starts at 10 a.m. in the topic of natural language processing. Thank you all.